Welcome back, everyone. In this example, we're going to talk about how to find the volume of a solid object using slicing and integration. So let's go ahead and jump right in and see how this is done using an example. So in our example, we are asked to find the volume of the solid that is created by rotating about the x-axis, the region bounded by the three curves, y equals the square root of x, y equals 0, and x equals 4. So as always, to help us figure this problem out and to set everything up, we're going to need to visualize our situation and our object here. So let's start by doing that. So we are told that the region we are eventually going to rotate around the x-axis is created or bounded by these three curves, y equals the square root of x, y equals 0, and x equals 4. Remember, y equals the square root of x is going to look something like this. Y equals 0 is just our x-axis, so maybe we don't even bother drawing that one in. And x equals 4 is a vertical line going through the x value of 4. So let's say that's right about there. And so our region is just this small shaded in blue region that I just drew. And so we're not trying to find the area of that region. Instead, we're doing something a bit different here. We're thinking about taking that region and rotating it, spinning it around the x-axis. And the idea is it's filling in all of that space as it gets spun around the x-axis. And that's going to create this solid three-dimensional object that we want to try to find the volume of. And so if we do spin this region around our x-axis and have it fill in all of that space as it spins around the x-axis, we end up creating this little solid object that'll have a flat bottom, if you think of the right-hand side as the bottom, and it'll eventually be what we call in a higher class a paraboloid. So we have this little three-dimensional object we created by spinning this two-dimensional region around an axis. And so now what we want to do is use integration to help us find the volume of that solid object that we just created. So we're going to take a small slice out of our object. That'll give us a small three-dimensional piece that we could put back together with all these other little slices to recreate our object. We will then find some way to approximate the volume of each of these little slices or pieces. Then we can add all those approximations together to approximate the total volume of our object. And then to improve our approximation, we'll use more and more slices, making them thinner and thinner. And you can kind of see where this is going. We're going to end up taking the limit of some sum of slices, which will turn into a definite integral. And so for this object, we want to think about taking a vertical slice out of our object, and that's going to be equivalent geometrically to taking some small horizontal strip, like one of our little approximating strips or rectangles, and spinning just that small rectangular strip around the axis of rotation. So what is that going to create if we take that slice and pull it out of our object and look at it independently? Well, I'm not the greatest artist here, but I think this will get the job done. We're looking at kind of a semi-side profile of our slice, and what that is going to give us is a disk. And we can also think of each of these disks as a little circular cylinder. And so now remember, we're trying to find the volume of each of these small little slices. We're going to add all those volumes up to approximate the volume of our entire object. So how do we find the volume of a slice or the volume of a disk? Well, we can think of it as a circular cylinder. The volume of our disk is going to be just like the volume of a circular cylinder, the area of the base times the height. And so we can think of that as pi r squared, that's the area of the base, times our height. Let's call it h for now. And so now to make any more progress for finding the volume of this approximating slice, well, we have to figure out how do we express r squared and h in terms of our function and these variables of x and y. Well, if we think about the width of the slice we took here, just like in all of our previous pictures, that's going to be some small change in x values. So that'll be our delta x. And now what is delta x representing in our volume formula here? Is it the radius or is it the height? Those are really kind of the only two options we might have to work with. Well, remember, we took the slice and this is the side profile of it. We usually view our circular cylinders as kind of tilted 90 degrees to the right or to the left. And so that delta x value, which kind of looks like a width right here, once we pull our slice out and turn it on its side, is actually going to represent h, the height of our disk in our little formula up here. So we can approximate the volume of each of our disk with pi times the radius squared times the height. And here the height of our disk is that delta x quantity. So the last thing we are missing is the radius of our slice or disk. And so the radius is just going to be this little vertical distance in the picture that we have drawn here. You can always think of the radius as the distance from your center, or in this case our axis of rotation, to the edge of our region or to the edge of our solid object. And so we can see that the distance from our axis of rotation to the edge of our solid object is equivalent to the distance from our x-axis, since that is our axis of rotation, to the top of our curve that created this region that we rotated. And so what is that radius value? Well, it's this vertical distance. That is our radius, but that is given by this y value. And so the radius of each of our slices, because right, if we look at this slice near x equals 0, it'll be a much smaller slice than one close to x equals 4, so they have to change. They're going to change as functions of x. That's why we're going to eventually integrate with respect to x. But the radius as a function of x is given by the square root of x. That gets us the y value, that height value for some point on our curve that created our original region that we rotated. But our formula for the volume of the disk is not just using the radius value, it's using the square of the radius value. So pi r squared is going to look like pi times the square root of x squared. And we can simplify that. The square root of x squared is just going to be x itself. So now we know we can approximate the area of one of our small little slices using pi times x times delta x. And so now if we want to approximate the total volume of our three-dimensional object, we have to find the volume of all those little slices and add those together. So maybe we start with n slices. So this is telling us we're going to have to add the volume of all of our little slices together. And so now the terms inside of our sum here have to describe the volume of each of our slices. But that's what our work above helps us do. So it's going to be pi times, and technically this would be like x sub k star, times delta x, where x sub k is just some sample point in that small subinterval of x values. Well, when we take the limit of our Riemann sum here, it's going to converge to a definite integral. Our limits of integration we can see from our picture are the x values from 0 to 4. What happens to the terms inside of our sum? Those become the integrand of our integral. So we're going to have pi times x times not delta x. When we take the limit, that becomes the differential of x. Oh, now the integral we have set up truly does represent the exact volume of the solid object we get by rotating our region of interest around the x-axis. So now to find that exact volume, we just have to evaluate our definite integral here. So our antiderivative will be pi over 2 times x squared. We have to evaluate that at 4 and 0 and take the difference. And when we do that, we end up with 16 pi over 2. Or simplified to just 8 pi. So now we know the exact volume of this solid object is 8 pi cubic units, whatever the units were. We didn't have any units in this problem. And so there's a large family of problems that are similar to this one, where we create some three-dimensional object by spinning a region about some axis of rotation. And our setup work was for this very particular example and problem, not for like the general situation, but we can generalize from this first example. And what we can kind of see is no matter what our region originally looks like, by spinning it around some axis of rotation, it's going to create this circular shape to that region. We then are going to look at different types of cross sections for the solid object that we create, depending on how our axis of rotation is oriented. We might look at vertical slices like we had here, or we might look at horizontal slices, just depending on how everything sets up. The idea is we want to slice it in such a way so we get some kind of disc-like object that we can remove after making that slice. We want a disc because we can approximate the volume of a disc very easily just using the area of the base times the height, the area of the base we'll have to express as some function involving the equations that describe our region, and the height is going to be either delta x or delta y, depending on what type of slice we have made. In this example, we took like a vertical slice out, and we were working with a delta x and with respect to x. In the other situation and setup, we might take a horizontal slice out. In that case, the height would be a delta y, and we'd be working with respect to y instead.